So here is a summary for all the elements that we can see in AC circuits. So here we have resistive element, here we have capacitor, and here we have inductor. The relationship between voltage and current for a resistance. Please don't forget these relation are has a direction. So if you assume the current is entering the positive, because all these elements are following a load notation, and load notation means that the current I is entering the positive of the voltage, you can write down that V equals Ri. This is the equation or Ohm's law for resistance. For capacitor, we have a differential equation that relates the current to the voltage. Again, don't forget that the current is entering the positive terminal of the voltage. Also for the inductor, we have a differential equation that relates the current to the voltage. And to use this equation, you have to assume that the current is entering the positive terminal of the voltage. All these equations here, this equation or this equation or this equation is called time domain because it's a relation between the voltage as function of time and the current as function of time. So these equations are the time domain equations. We can move this equation into frequency domain. So Ohm's law becomes V equals Ri, but here it's a vector. Vector means magnitude and angle. For inductor, we can write down that V equals minus, for capacitor, we can write down that V equals minus J over omega C multiplied by I. For V, we can write J omega Li, and as you can see, this is the frequency domain that we have linear equation. We don't have differential equations, so we can use complex number calculation. The relation between V and I, as magnitude for energy storage elements, we call it reactance. So the reactance is the ohmic resistance of an energy storage element. So the relation between V and I as magnitudes for an energy storage element is called X. So for a capacitor, the reactance is 1 over omega C ohm. So the reactance, it's ohmic resistance of an energy storage element. So it's not defined for a resistance because the resistance is not an energy storage element. For inductor, the reactance will be omega L. So if you have a capacitor C in farad, 1 over omega C, it's ohmic resistance, the ohmic resistance of the capacitor. And this is the relation between the voltage magnitude and the current magnitude across the capacitor. For an inductor, the relation between the voltage across it and the current through it as magnitudes, XL is omega L. So if you have L in Henry or C in farad, if you find 1 over omega C or omega L, this is the ohmic resistance in ohm. And now you got rid of farad and Henry. The impedance is the resistance taking into consideration, or the ohmic resistance taking into consideration the time shift, the time relationship. So the impedance has the time information, and this is the difference between reactance and impedance, that the reactance is the ohmic resistance, it's the relation between the magnitudes, no time information. But for the impedance, it's what is the relation between V and I taking into consideration the time shift between them, or the angle shift. So the impedance for a resistor is R angle 0 because there is no angle shift. The impedance for a capacitor is 1 over omega C, and don't forget that the capacitor here has an angle negative J between V and I. So the angle here is negative 90. For the inductor, the magnitude is omega L, and the angle here is the relation between V and I is J omega L. So here we have positive 90. So here we have positive 90 because we have positive J. Here we have negative 90 because we have negative J. For resistor, we said that I and V are in phase. For capacitor, I lead V by 90. For inductor, I lag V by 90. Now let's do an example on AC circuits. So we have this circuit. This circuit has resistive element here, R, it has L, it has another L, R and C, and it has two sources. So the first source is 120 cos 100t plus 15. The second source is 1.5 cos 100t plus 135. The first part you need to see is that make sure that the two sources have the same time domain function. So make sure that the sources are both sine or the two sources are both cosine. And as you can see here that the frequency is 100. So make sure that both sources have the same frequency. And this is the only case that we will consider, that the two sources are running from the same frequency. As we said, to move from time domain to frequency domain, we consider that the frequency is the same. So how we can deal with different frequencies if we have two sources with different frequencies? The only way to solve this situation, but we will not do this in this course, is to use superposition. So you consider one frequency at a time. But all the sources that we will consider in our course will be of same frequency, which is a logical assumption. So here in North America, the frequency in North America is 60 hertz. So it's one frequency. All the sources or all the outlets in North America have the same frequency. So it's an acceptable assumption that practically the frequency is constant and all the sources will have the same frequency. So to solve the circuit, the first thing we need to do is to move from time domain to frequency domain, or to represent the circuit in phasors. So first here we have a source VG, or a voltage source. So the voltage source has a magnitude of 120 and has an angle of 15. So we can write down 120 angle 15 degree. The current source has magnitude 1.5 and the angle 135. So first make sure that all the sources are sine or cos. If one source is sine, the other source is cosine. Convert the cos to sine or convert the sine to cos. Make sure that your reference wave is the same. Second, make sure that all the frequencies are the same. Then you can convert each source into its frequency domain version. Sometimes, as we will see later on, we can divide the magnitude by root 2, so we can move to RMS value instead of peak value. So this value is the maximum of the sine wave. We can move it to RMS by taking the maximum and divide it by root 2. So usually the frequency domain is done using the RMS, and usually the time domain is done using the maximum values. Okay, this is like a default or notation. Why we are doing this, we will learn this when we cover power calculation. Okay, but this step here, we can do it or we cannot do it. That doesn't matter. It will not affect the answer, because after you go back from frequency to time, you will multiply the RMS by root 2, so you can go back to time. So if you divided or didn't divide, at the end you will multiply again by root 2. But let's keep one convention, and the convention is when we move from time to frequency domain, we will divide by root 2. So let's see here the solution here. I divided the solution here by root 2, and this is the default that we will use. Now we converted the sources into the frequency domain. So this circuit is in time domain and this circuit is in frequency domain. Now how we will convert 10 ohm into frequency domain? We said that the resistance will have an angle 0, so it will be the same. It's already in ohm. So how we will deal with 0.2 Henry? So any L, we will convert it to J omega L equals J. Omega is 100 and L is 0.2, so this will be J20. So this L will be J20. And similarly, this L will be J40. This capacitor here, so the capacitor, to convert the capacitor into frequency domain, we use minus J over omega C equal minus J over 100 multiplied by 0.1. So this will be sorry, 0.01, correct? So it's 1 millifarad. So it's omega C. So capacitor is, oh okay, 1. So here we have 100 multiplied by 0.001. So this will give us minus J10. So this capacitor will be minus J10. So to convert L, you calculate J omega L. To convert C, you calculate minus J divided by omega C. The unit for J omega L is ohm. The unit for minus J over omega C is ohm. So this unit is ohm, this unit is ohm, this unit is ohm, this unit is ohm, this unit is ohm. So your circuit now is totally in ohms. So you can use Ohm's law. So no more differentiation, no more integration. So you don't need to solve differential equation here. So let's sketch the circuit again. So let's first copy the circuit. So here, instead of this value, so I will remove these values from here, and I will write its ohmic value. So here we have J20 ohm, here we have minus J10 ohm, and here we have J40 ohm. And we have this source as 120 divided by root 2 angle 15. This source is 1.5 divided by root 2 angle 135. This is what we have here. Now these two values are in ohm, and if you have two resistances connected or sharing the same current, they are connected in series, so we can add these two together. So we will use a box symbol to represent an impedance, and impedance means a mix of RLC. So whenever you have RLC mix, you sketch it as a box. Inside this box there is mix of elements. So this impedance will have a value of 10 plus J20, and its unit is ohm. Then we have a current source here. Then we have this one plus this one plus this one will be 20 plus J30, and the unit is ohm. And we have a voltage source here. So the value of this source is 120 divided by root 2 angle 15. The value of this source is 1.5 over root 2 angle 135. Now we will deal with this circuit as we dealt with a DC circuit. So how many elements we have? We have 1, 2, 3, 4 elements. So how many unknowns? So the number of unknowns is 4. We have 4 unknowns. So how many equations we need? We need 4 equations. So how we will get these 4 equations? We will get these 4 equations using KCL and KVL. So how many KVL we can do? We can do 2 KVL. So we can do 1 KVL here. We can do 1 KVL here. How many KCL we can do? We can do 2 KCLs. We can do 1 KCL here, and we can do 1 KCL here. So these are the 4 equations. So these 4 equations can be obtained by doing 2 KVL loops and 2 KCL loops, and you are done. You can solve the circuit. The only difference between AC and DC that the calculations will be done in complex numbers. So DC is a special case from AC. So DC is an AC circuit with all the angles 0, because you have only resistances in DC. AC, you are doing the same as you did in DC, but you have magnitude and angles. So you are doing this as complex number calculations. So let's see how we can deal, or how we can solve this circuit here. So let's copy the circuit. So how to solve? So we will follow same steps as in DC circuit. only difference is all numbers are complex numbers. Okay, so let's see how we will solve this circuit. Okay, let's see how we will deal with this circuit. So how we deal with circuits, we said with circuits, we start by assuming currents, and after we assume currents, we apply KVL. So let's start by assuming currents. So here we have a voltage source. So this voltage source will have current going out of it. So the current will be leaving the positive terminal because it's a source. And we can name this current as I source. And the current going from the source is the same current here. It's like we applied KCL at this node. So we said that we will assume the current, and while we are assuming currents, we will do KCL. So the current I source will enter this impedance, so the current here is I source. Now instead of naming another current here as say I2, I3, and then we have two unknowns, I source is unknown and this I2 is unknown, but we have these two currents are related with the equation of this node, let's apply KCL. That's why when we said the steps to solve any DC circuit, first assume current direction. While you are assuming current direction, apply KCL, and after you finish this, just you will apply KVL. So this will reduce our variables from having 4 unknowns into having just 2 unknowns, because already we used the equation for KCL at this node. So instead of defining one current here and another current here, we said already these two are the same. And instead of defining a current here and another current here, we can say this current here is simply I source negative 1.5 divided by root 2 with an angle 135. So I source is entering, we are subtracting or losing part of it here. This is the remaining one. Now, we did the first two steps by assuming currents and applying KCL. The second step here that we will do is applying KVL. So how we will apply KVL? So I will copy this loop here. So we don't have the circuit to be okay. So instead of doing this, I will sketch. So I will sketch loop 1. So what I have in loop 1, so this current source is 1.5 over root 2 angle 135. The current here is I source, and the voltage here is 120 divided by root 2 angle 15, and this impedance is 10 plus j 20. Now we need to assume the voltages, okay? So the current is going in this direction into an impedance, and impedance means load, because RLC will be treated as load. So this current has to be entering the positive terminal of this load. And here we have a current source. So the current source, you are given the current. So the unknown will be the voltage, and we will assume the voltage for any source. So the current is leaving the positive terminal. So we will assume here is positive, here is negative, and this is the voltage of the source, and this voltage is unknown Vx. Now we can apply KVL in this loop. So we will go in this direction. So when we go in this direction in loop 1, we will have negative here, positive here, and we have negative here. So we can write down negative 120 divided by root 2 angle 15, positive, because we have positive here, 10 plus j20 I source, negative Vx equals 0. So here we have one equation, and this equation in two unknowns. The unknowns are I source and Vx. Now if we go back in this circuit, how many unknowns we have? The number of unknowns we have is the current in this branch here, the voltage across this source here, and the current in this branch here. So we have 1, 2, 3 unknowns. But don't forget that this current number 3 is I1 minus the current of this source. So this is not an independent unknown, because once we know I1, the current 1, once we know 1, we will subtract this current from it so we can get this. So the minimum number of unknowns for this circuit is 2. The 2 are the current of this source and the voltage across this source. These are the 2 unknowns. And these are the 2 KVL loops that you can see. Now let's continue. So this is the first equation that relates I source to Vx. Now let's sketch the second circuit, or the second loop, loop 2. So if we sketch loop 2 here, so here is the source. Don't forget we assume the voltage here Vx. The current going here is I source minus 1.5 divided by root 2 angle 135 degree. This impedance here is 20 plus J30. So this current will be entering the positive terminal here of the impedance. So if we go in this direction, so we will see positive, then positive. So we can write down positive Vx, positive 20 plus J30 multiplied by I source minus 1.5 divided by root 3 angle 135 equals 0. And this is equation 2. Now we have 2 equations in 2 unknowns, and the unknowns are I source and Vx. Now what if we added the 2 equations? If we added the 2 equations, you can see that Vx will cancel Vx. And this physically, that if you take the outer loop and you write KVL for the outer loop, so you are bypassing the source here. This is what we did when we added the 2 equations together. So we can add the 2 equations together. So let's copy this equation here. So this is the first equation here. And this is the second one here. Now if we added the 2 equations, so we will get 120 negative divided by root 2 angle 15 plus 10 plus J20 I source plus 20 plus J30 I source minus 1.5 divided by root 2 angle 135 equals 0. This is root 2. As you can see, we have one equation in one unknown, and this unknown is I source. Once we solve this equation to get I source, we will go back to one of the 2 equations, I1 or I2, to get V source. So here we can find I source. So we will move this to the other side. So we have 120 divided by root 2 with an angle 15. And here we have this negative. It will move to the other side also as positive. So positive 1.5 divided by root 2 angle 135 multiplied by 20 plus J30 equals 2. I will take I source as a common factor. So we will have 30 plus J50 I source. So we can calculate I source as the division of these two. Okay, so just I will take these two numbers. So this will be your I source, and we can calculate this using your complex number calculation. So we can, using your calculator on complex number mode, so we can calculate I source, which is named here as I2. Okay, so let's copy this one here. So this is I source. Once we have I source, we can go to 1 or 2 to get Vx. So from 1 here, if we go to 1, so Vx can go to the other side. So we can find V source as, sorry, Vx as 120 negative divided by root 2 angle 15 plus 10 plus j20 I source, and here we have I source. So from this we can get Vx, which will be the value we have here. And after we get I source and Vx, we can go back to time domain. So if we want to go back to time domain, so let's copy these. So don't forget that the problem started with time domain, but we moved the problem to frequency domain to be able to solve it. Okay, so we can return these two values into frequency domain again. Okay, so if we take this value here, this is I source, and let's take this value here, this is V source. Now this is the solution in frequency domain. If we go back to the original equation, so we have the frequency is 100 and the function was cos. So if we go back here, we can write I source of t as 0.80183 multiplied by root 2, because when we moved from time to frequency, we divided by root 2. So when we move from frequency to time, we multiply by root 2, cos 100t minus 41.186 degree, and Vx of t, the voltage of the current source, will be 67.132 root 2 cos 100t minus 166.976 degree. This is in ampere and this is in volt, and this will be the solution in time domain. So the idea to solve AC circuits is to move from time domain to frequency. Then we solve in frequency, because in frequency we will not deal with differential equations, and then we will have all the equations as complex number calculation, which you can do using your calculator. And after we do the calculations in frequency domain, we can go back to time domain. So I prepared some slides here on how you calculate these values in steps in the calculator, using the calculator, and I posted these online. So to calculate the current, so here are the steps, and these steps are 1, 2, 3, what you will do in your calculator to do this calculation. And these are the two types of calculators that I'm using. The two calculators are Casio, or if you have TI calculators that can do complex number calculation, but the one I have is Casio. So these are the steps. So you start by selecting the mode as complex, and then you write down the equation, and after you write down the equation, you will get the answer. And because this calculator is one line, so it will give you the magnitude. To get the angle, you press shift plus and equal. it will give you the answer as r and theta, because the default here is rectangular. So this answer is rectangular. As you can see here, it is rectangular. To move it to polar, we press shift plus and equal. It will give you the magnitude, and to get the angle, you press shift equal. So this single line calculator, to get the other line, you press shift and equal. So this shift and equal will give you the second line. This calculator is much easier because, again, you will select the complex mode. Once you are in the complex mode, as you can see, you can write the equation as you see it, because it's two lines. And once you write the equation as two lines, if you press equal, you will get the solution here. And this solution, as I mentioned, it's two lines. So as you can see, there is a real number, then there is a negative, and there is an imaginary number here. So if you move with the arrow here, you will go, if you move with the arrow here, you can go here. So this is the real, and here is the imaginary. So if you move with this arrow, you will see the imaginary. Okay? I don't know how to cancel this. Now, here, as we said, the answer will be rectangular. To get the answer as polar here, you press shift, then you press 2, which will give you these options. Then you select r and theta, which is option 3, and you press equal. If you do this, it will give you, as you can see here, it will give you the answer as magnitude and angle. To see the angle here, just to press this arrow here. Okay, so if you press the arrow here, it can show you the angle. So I prefer this calculator, Casio FX 570 ES or 995, which has a complex number calculation. So I will post online these slides which show you how to use the calculator, and please, please, please take a moment and make sure that you can calculate this equation here to get this number. Okay, this is an activity you should do. So please calculate this using your calculator, and make sure that if you write down this equation here, you will get this value here. And also check Vx calculation. So I will stop this here. Hopefully you get an idea how to deal with AC circuits. Next lecture we will learn about power calculation, and see you next lecture. Thanks.